for this first problem here, determine the value of IT. I2, that makes the circuit interconnections valid. Assume that V is equal to 10 volts and I1 is equal to 3 amps. Okay, so we need to find I2, I2, draw this really quick. Solve for it. Okay, and then we'll write down the values. Volts is equal to 10. I1 is equal to 3 amps. Okay, now let's switch to the screen. Okay, there's goofy drawing. Need to find I2. And the voltage coming in through here is 3 amps. Well, it's safe to say that in the other direction would be I2, which is negative 3 amps. Let's see if that's right. I already forgot the answer, to be honest. Yeah, that's the answer. Right here. It's in the opposite direction. Okay. That's for the next problem. With the circuit shown, figure 2, determine the value of alpha. Figure 2, let's draw figure 2. Alright. So we have current here, current here, current sources in the middle, battery in the middle, which is equal to alpha. X. Trace the signal's origin. And we have I2, I1. Okay. So, what values are we given? You're given the voltage is equal to 2.5 volts. I1 is equal to 10 amps. And I2 is equal to 4 amps. Alright, let's switch. Okay, so this is what we should have here. What do we need to know? We need to know... We're trying to find alpha. So if we know we need to find I sub x here, we need to find alpha. Well, we know the voltage is equal to 2.5, which is equal to alpha. I sub x.
What? That's not even supposed to happen. Unfucking
Well, we know the current here, which is 4 amps, and then we see that there's an opposing current going in the other direction right here. We can say that that is negative 4 amps times alpha. Can't draw it very well. Equal to 2.5. We can divide the negative 4, and now we have alpha. 2.5 divided by negative 4. What does that give us? Negative 6.25. Does that match our answer? Yes, they rounded it a little, but same. Negative 6.2. Negative 0.625. Rounded to negative 0.60. Alright. Now let's go to the next set of questions. Alright, so this is KVL stuff. Kirchhoff's voltage, whatever. Basically, go clockwise. Clockwise. Yeah. Then a single circuit. You have to have the sum of all the voltages equal 0. And voltage at each different point can change depending on the resistor. So this is how this is displayed here, but in reality these would be resistors, and the central one, or whatever the source battery would be, wherever that's at. But, yeah, so let's draw this. So we're given voltages at very different points. Just writing all these numbers down real quick. V2 is equal to, oops, 9. This one is 2.75. So we're given the 3, we need to find the other ones. Okay. Let's go back to here. This is what I got written up right now. So we need to find here and here. So let's label all these. We'll label this one V2, V1, V2, V3, V4, and V5. Alright. We're going to do it that way so we can get our signs right. So, KVL, Kirchhoff's voltage law stuff. So this is one little circuit area right here, right? If we were to go clockwise. What I mean is that it's closed, like it's like one little triangle here. It's one little piece of like a puzzle, sort of. That's what his law states. And one little circuit that's closed off, if you go clockwise, right? Sum of all the voltages must equal 0. And the sum of the voltages, well, you'll have like a voltage source, for example, and they don't have it labeled like this, but you'll have resistors, right? And there'll be voltage drops across those. And the sum, typically you'll make the voltage source negative, like negative 20 volts, and you'll have different voltage drops across these resistors. And the sum of all those will equal 0. So V1, which is positive, according to the sign convention, plus to minus, plus V2 is positive, plus V3 is positive, is equal to 0. Right? So we know negative 4.8 is V1, 1.9 is V2, is equal to V3, is equal to 0. let's plus the 4.8 over, subtract the 1.9, and that will give us V3. Alright, V3 is equal to, let me go back real quick, 2.9. Yep, that math should add up to 2.9. Okay, and let's do it for the second part. So if we go clockwise from the top, this top here, follow it in a circle, right? V3 ends up being negative. V4 is positive. Plus V5, which is also positive, is equal to 0. Now let's plug in our numbers, negative 2.9, because this, V3 goes from negative to positive, plus V4, we don't know that one yet, plus V5. The number itself is given as negative. It's equal to 0. Now, plus 2.75 over, and then plus 2.9 over, plus 2.9, and that'll give us V4, which should correlate to some number 5 positive. Yep, 506. Yep, that's how you do that. Okay, so for the second part here, we're going to be using figure 1 again. Or figure, not again. Here, here's this figure. But we will be using figure 1. Okay. So we have currents here. Alright. So we're gonna draw all of this. I don't know why the box is really there. But they're there. We're just gonna draw the currents. Make it simple. I2. I4. Sweet. Okay, I drew them all, and we're given I1 is equal to negative 400 milliamps. I2 is equal to 0.5. We'll convert that to milliamps here, which is 500 milliamps. Let's go to 4. So we have these currents, these 3 currents. We know I2, but we need to find I4. So how do we find that? Well, Kirchhoff's current law states that when this current here, up here, that'll travel down, right? That'll go down, and then it splits off here. Well, these 2 currents, when it splits off, added together must equal the original current, which is 500 milliamps. Well, if we set them equal to 500 milliamps, is equal to negative 400 milliamps plus X, we put it as I4. This one's I2, and this one is, no, I2 is this one. And I1 is this one, right here, I1. So we need to find I4. So plus 400 over 900 milliamps is equal to I4. And this will make his law valid. Right? 900 milliamps right here. See? Matches up with the numbers we know. We convert it, 3 over. Alright, we'll get 0.9. So let's go to the next one. Figure 2. drama figure. Really quick on my iPad.
Hostile down! Not all of them? Then we keep moving.
Okay. So, and now we're given voltage is equal to 6.8. I have it drawn. I just need to write the numbers down. V sub x is equal to 3.5 volts. We're given R1. What is R1 here? This is R1. Resistance 1 is what the heck is this doing? Given R1, which is 2 ohms, I is equal to
Gotta react.
negative 0.5 amps. Okay. Determine R. Alright, let's go here. Alright, so we need to find this R here, and we're given these set of values. Okay. So how do we do that? Well, we could do Kirchhoff's voltage law, which states that the voltages here, all of them added together, must equal 0, right? So we have V, the original V, plus V sub x, which is the voltage drop across this resistor here at R1, plus, right? What is resistance equal to? Right? What is R? How do we sub that in? Well, voltage is equal to R times I.
One down!
Right. That is what it is equal to. So if we can find Ri, we can solve for R plus Ri. That is equal to voltage. Right? If we can find the current traveling through, we can find R. So we know this amp source here is traveling up and through here, right?
Here comes more of them.
Which is negative. But we need to find the current somehow. Well, there's one way to find the current. We know the resistance here at R1, right? And we know that voltage is equal to R times I. Well, voltage over I is equal to R. No, that's not what it would do. Voltage over R is equal to the current I. Right?
Here comes more of them.
And the current going through here is the same at points R and R1.
Everyone down!
So since we know the voltage is 3.5
Reloading!
divided by 2, the current must equal 1.75 is equal to I. So we know V will make it negative, so that the voltage sources from the other two, when added, will make it 0. So a negative V, which is 6.8, we'll add it over and make it positive on the right, minus 3.5, which is 3.3, okay, equal to R. We know I now, which is 1.75. So 3.3 divided by 1.75 is not going to be the right number. Where we messed up was is we forgot. So we have to worry about this current here too, because the current breaks off. So if we were to say the current going this way, well, it's in the opposite direction of 0.5. And the current going here is 1.75. So you're going to use Kirchhoff's current law, which states this current going this way and this one going this way. Well, what's the current originally when it goes here and then it breaks off here at this point? For example, it's something like this. It splits to 0.5 and 1.75. 0.5 being the opposite value of this current here, because it's negative going this way and the opposite, it would be going positive going that way. And you can reverse it like that. So the actual total current going through that first resistor is 0.5 plus 1.5 plus 1.75, which is 2.25. I 2.25.
Through the building.
3.3 divided by 2.5 gives us our answer. 1.46 March. I messed up a little. Around a little bit, get it closer. But that's our answer. Okay. Did I do 3? No, but I could probably do it, right? Okay. I'm erasing that stuff real quick.
Let's find a way out of here.
Okay. So we're given I is equal to 3 amps. R1 is equal to 19.2 ohms. R1. R2 is equal to 10.1 ohms. And alpha is equal to 0.35. Okay, and we need to find V naught. We're using this circuit here. So I'm gonna draw it real quick.
Adams, Lugo, do you read? It just keeps getting better. Find a rifle fast.
Okay, I'm just drawing the circuit real quick. Let's go back here.
Do I sound okay?
So we have a voltage source here, and we have V naught here. Okay. So the voltage is flowing from here to here, positive or negative. It's a positive sign. And we need to figure out what. How will we do that? Well, we know alpha. We don't know Vx. We're not given that. But we do know Kirchhoff's voltage law. We know this voltage, right? And we're given the resistance and we're given the current. That's all we really need. So we have alpha, V of x, which is the first voltage. From positive to negative, we're going this way. I'm gonna make this negative so that when we add R1 and R2, they cancel out to equal 0. So plus R1 times the current we showed that number is 19.2 times the current 3 is 57.6. Okay. Odd numbers. 10.1 times 3, which is 30.3. Some big numbers. All right.
He's fine, Adams. So am I. Need to
So
get
let's
work.
find.
Just saying.
Are we given V of x?
I know.
Let me see.
Got a lock on the signal, Lugo?
Go back to the problem.
Yeah. Then let's move.
Nope.
Threat eliminated!
Where's I sub 0 at? We know the current. Are we given the current? Yeah, we're solving for V naught. That's for question 2. We're not worried about that. Okay. Yeah.
Reloading! Keep an eye out!
So, let's see what this yields us. So positive alpha.
Distractors over here! Get him before they call for backup!
Positive alpha.
By the shipping container! Put him down!
Let's add this together. 87.9. Well, do we know alpha? We do. 87.9 divided by 0.35. It's a big number.
Throw on the sticky!
51.14 is equal to V sub x. Okay, since we know V sub x, right?
Hostile down!
We have 87.9 as the total voltage source going around. But according to the diagram, V naught is from this sign convention, which is the opposite of what we have here. So V naught is negative. We're going to take a gamble. We're going to say V naught, this point here, is equal to the voltage source, the original voltage source. Right.
Target down.
87.9. Obviously in volts.
Adams, get that door open.
Incorrect.
Shit, what is it? Multiple contacts behind us.
What's that?
Walker, there's a turret over there. Cover me while I get this door open. No problem. I can help, boss. Just give me a target. Priority target! Take him out! Target neutralized! Snipe that hostile! Sure thing! Taking it down! Got the target! Lugo, counter snipe!
Let me think of what I thought. Alright, I found out how where I went wrong with the problem. So, okay. So, this here, this voltage source here, V sub x. We're given V sub x here. Alright, let's ignore everything I've done so far. Well, the voltage drop here across this is equal to R2 times R is equal to V of x. This is equal to the voltage. There. And we can sub that in there, and we can say alpha is times R2 times R. That'll give us the voltage there, which is 10 point something. So we have negative alpha. Oops. R2 I plus R1 I plus R2 I equals 0. Oops. R1 I plus R2 I is equal to alpha R2I well, we know the current one in R1, which is R1 19.2, say 19.2 times 3.
They're everywhere! Watch your flanks!
Oh, what the fuck? Oh, wow. Dude.
Okay. We can get rid of I, right? Because I is everywhere. So we have R1 plus R2 is equal to
I feel like daylight's
two.
coming back. There. Daylight's coming back.
Like
This
this?
time it'd be pitch black.
I guess.
It's not something I want to think about right now.
Like, it was looking like this with
They spot us?
So R2 is equal to 10.1 times 0.35.
Open fire!
Oh, we know the currents aren't the same everywhere. Can't do this. I2, 1, I2. Well, the current going through R1 and R2 should be the same.
Take him
Times
down!
alpha 0.35.
Reloading!
The current should be the same for that substitution.
Tango down! They're everywhere! Watch your
here. Voltage of dependent source. How do we figure that out? We have a current 3 amps.
Empty that bus. Flash and clear.
What is V?
Target neutralized. Reloading.
So the question is, solve for V. Well, let's just do Kirchhoff's law. But instead, we add V0.
One down. That's okay.
But it's
Save.
negative. Really not that equal.
Sticky grenade out. Got one. Don't worry. They'll be back. Hey, fuckface. Tell the 33rd to stand down. This is helping no one. Sorry, but I answered your higher authority. You kept walking. Oh, so you remember me now? I do indeed. I'm not the only one.
Okay, so 10.1 times 3. We have 90.2 times 3.
Cool little bunch of on-move against trained soldiers. You didn't know this was gonna happen. Maybe the loss was worth the gain.
77.3. I doubt it. No way. That's right. You're lying. I figured out how to solve it. It's crazy. Okay. So to solve this question, start from the beginning. So the current is 3 amps everywhere. So we have a voltage source here called V0. Positive and negative. So we need to find V0. So if we go this way, right, plus negative. The sign convention, let's review, would be, well, before we do that, we need to find what Vx is. When you see Vx is V2, well, what is voltage equal to? Resistance, R2 times current, which is I. We know those two, which is equal to V of x. We can sub that in, like so. And now we can do Kirchhoff's voltage law. So we have alpha R2 times current minus V0, because it's going against the other signs, plus R1 times current plus R2 times current is equal to 0. And we can solve all of this, and set it equal to that there. can find the voltage there. That's how you solve that problem. Okay. Alright. Since I don't have enough time for the other ones, I'll do 13. Which makes sense to me now. So, if you look at the figure, right? Question asks, what is the predicted, use the model, predict the power that the device will deliver to 800 ohm resistor. What is power equal to? Power is equal to voltage times current. So I need to find the voltage and the current going across the third one. So let's draw a diagram. So we have to go here. So the device, if you go to the video, what it actually looks like is we have a 440 volt here, plus minus. We have an 800 ohm resistor here. And from the question, it wants to know, without, well, this is the device here, right? Without the device, plus the device, what is the power being delivered to an 800 ohm resistor over here? So we have two 800 ohm resistors, right? And we know the current, which is, the current is 0.5 milliamps, if I remember. That is the current going across the first resistor when there's one resistor, right, in the device. So let's go back to the basics. Right, so we have 40 V, Kirchhoff's voltage law, 40 volts plus, we'll name this R1, R2, R1 times this current plus R2 times some current. We know R1 and R2, which is 800 ohms. What is the current now, since we have two resistors? So, make this negative 40, because the sum must equal 0. We can't have them all being positive. So 40. Factor out the resistors because they're actually the same. So factor out 800. I. Actually, no, it'll be 800 I plus 800 I. You can add things with the same units, which is 1600 I is equal to 40. Divide 1600. 40 divided by 1600. And you'll notice that the original amperage is 0.5 amps, which is like 50 milliamps. Is now cut in half because we have another resistor, which is the same. Right, so this number here is equal to 0.025 amps. Right? So we know the current. Power is equal to voltage times current. So we know the current going through the second one. But what is the voltage, right, going through that second current? Well, the voltage going across there is 0.025 times the resistance. 800, which is 20 volts. 20 volts going across that resistor. So 20 times 0.025 is equal to 0.5. Right, 0.5 volts. And that's your answer. That's what you want. And now let's go to the next one. It's a little tough one, I ain't gonna lie. So, it's a lot of work for this one. plus minus 20 volts.
In the dirt too? You keep pissing me off. I'm gonna shoot you both of you. Shut the fuck up. Now let's go.
V sub x. Plus minus V naught 300 volts. Okay. So the question's asking, what is the power delivered by the voltage source? Well, the voltage source is here, right? Where does it need to be delivered? Well, we have a second whole element on this side, right? A whole different node. So total voltage source coming from this side is 20 times, what is it? Power times the current. We need current. Well, the current from here to here is equal to original voltage plus R1, R2. I'll label this one R1, R2, and the current across those will be equal. All the resistors in one little circuit thing have the same current. So, negative 20. 20, plus it over, 20, equal to R1, I, well, we can just add them together, since they're the same, whatever, so it'd be like 600 I is equal, so 20 divided by 600 gives you 0.0333 repeating amps, times this number, is 0.666 watts. You can round that to 0.667. Boom. I didn't switch my screen.
And you're fighting in the dirt like a couple of goddamn kids. Delta operator.
Here's my work.
Fucking act like it.
Here.
All right then. We good?
Becomes negative 20 plus
Lugo.
450 I.
Good.
Plus 150
Let's
I.
keep moving.
Plus 20 over 20 is equal to, add those two together, 600 I. Divide the 600 over, and you get your current that you need, because we're looking for the power being supplied to this element over here, going across, and the voltage leaving from here, right here, is just going to be 20, right? Because once it meets here, it's going to be 20. So 20 times the current leaving here, after the current goes through these first two resistors, which we can find from Kirchhoff's voltage law here. So 20 times 0.033333. That's that. Okay. This will be like part one. I need to do the other questions.